Okay, thank you so much, Pierre. Hi everyone. First of all, thank you so much for the invitation. I'm going to talk a little bit about knowledge graphs and recommendation systems, specifically for scientific and biomedical fields. Okay. So the outline of the lecture is a small introduction and motivation. Then I will present the fundamentals of recommender system, graph recommender systems, and then I will talk a little bit about some use cases. So starting with introduction and motivation. So scientific knowledge is growing faster than humans can process. This is a universal truth. Some examples is PubMed, where more than 38 million articles are already published. Thousands of papers are published daily. And also we have millions of biomedical entities to discover, to study, to provide information to the researchers. Scientific discovery can be modeled as a recommendation problem. Usually, the researchers ask some questions as which drugs should I investigate, which proteins interacts with this molecule, which microbe could inhibit this pathogen, which paper should I read? Okay, so we have this pipeline, researchers, candidate entities, and the rank of the recommendations. What makes these recommendations so difficult? There are some challenges, sparse data, limited interactions, heterogeneous information, complex relation between the entities and between different fields, and of course, this need for explainability. Why semantic matters? For example, we can have a pathogen a microbe B, a crop C, article E, and a researcher E. And these entities are related in some ways that traditional recommender systems cannot easily model. Okay. So starting with the fundamentals of recommender systems. What is a recommender system? The definition, so the main definition is a software tool and techniques that provide suggestions for users that are most likely of interest to a particular user. So suggestion of items that are most likely of interest to a particular user. What can be this user? Usually people associate users to users of a system, okay, of clients of a platform, but these users can also be researchers, clinicians, patients, laboratories, institutions, devices, and so much more, okay, as we will see along this lecture. The items, the most known items are movies, music, products, because there are a lot of data sets in these specific fields. But these items also can be scientific papers, genes, proteins, drugs, disease, microbes, images, treatments. So everything that is a scientific item. So everything that can be studied by researchers. The interactions, we are used to see interactions as ratings. So some user provides some classification to a product, but these interactions can be much more as citations, purchases, clicks, co-authorships, experiments, and a lot of different types of scores. Well-known platforms that you probably know very well that use recommendation algorithms is Spotify to recommend music, Netflix to recommend TV shows and films, also IMDb, and Amazon to recommend different products. So if you go to your Amazon, you will see something like deals picked for you, or if you go to Netflix, you will see because another user very similar to you also likes this show. Probably you also like, and the platform will recommend this to you. Main approaches in recommender systems. There are a lot of more definitions. I specifically also always like to show these three different approaches. So collaborative filtering, content-based, and hybrid. But of course, if you read several surveys, you will find different definitions, but these three are transversal to usually to each study. So collaborative filtering is where you find similar users. And when I say similar users, this means that these users have similar tastes. So they rated the same items similarly. Okay. So in this example that I have in here, if both read one article, for example, uh, and if she read another article, this article will be recommended to him. Okay. Some more examples specific to biomedical fields. Researchers publishing on similar genes may also be interested in the same diseases, and clinicians treating similar patients may select similar therapies. Advantages of collaborative filtering. They are domain independent. So as long as you have a column with user, item, and rating, what is the user, what is the item, what is the rating, you can directly apply these collaborative filtering algorithms. And they often achieve strong predicted performance. So usually we get very good results with collaborative filtering approaches. Some limitations, we have a cold start problem for both users and items. So if we have a user that didn't rate any items, it's very difficult to provide recommendations. We can use the most popular, for example, but this recommendation will not be tailored for this specific user. And we have the same problem for new items. So if we have an item without any rating, it will be very difficult to recommend this item to another user. Another limitation is data sparsity, but this is transversal to all recommendation approaches. We deal with a lot of sparse data. And sometimes it's difficult to explain the recommendations. Of course, if we use simple methods, we can always say that there is similar users that also like this item. Okay, now another approach is the content-based. This is a more field approach. So this approach recommends items similar to those previously preferred by the user. It's not dependent on other users. So, for example, if I have a user that reads some article, we will find similar articles, similar in the content, and we will recommend this article to the user. These approaches need to use data related with the specific item. So some examples from the biomedical field, it can be metadata, semantic annotations, ontologies, and I will show you two examples where ontologies are used as features for the items. We can use molecular descriptors, text embeddings, and biological features. Some examples, so recommending chemical similar compounds, suggesting biological related microbes, finding articles with similar semantic content, for example. The advantages of this approach, it's more interpretable. So I can just say that, okay, this item is very similar to the one that you already liked. It works better with sparse interactions, and it can actually recommend new items. So Imagine that I have a new item in my system. This item doesn't have any rate, but I can still recommend because I'm comparing the features for the item, okay, not the ratings. Some limitations, and for me this is a big one. It requires a high quality item description, and sometimes in scientific items it's very difficult to find the right features for the content-based algorithm. And it also may generate over specialized recommendations, and I will end up recommending always the same items for the user. I will not have diversity. I will not have serendipity. I will not have diversity in my recommendation. Depending on the field, this can be a good or a bad thing. But for try to mitigate the limitations from both collaborative filtering and content-based, we can create these hybrid approaches between collaborative filtering and content-based. And for example, the problem, if I combine collaborative filtering and content-based, the problem for cold starts that come from the collaborative filtering for new items will be suppressed by the content-based part. There are a lot of different ways to combine the, these main approaches. Now, one very, very important thing in the recommendation system is the feedback. Usually here I write users feedback, but today I just say feedback because this feedback may not be from a specific user, as you will see, because my users may be diseases or genes or chemical compounds, okay? But this feedback is very important, so we can associate one user to an item. We have two specific types of feedback, explicit and implicit. In the explicit feedback, the user will directly evaluate an item. So with a thumbs up and thumbs down, with a star schema, and the user will specifically tell us, I really liked this item or I really hated this item. Okay. We can also collect this information, for example, from reviews. It's also very, very useful. In the implicit feedback, this is a more trickier because we will infer the behavior of we will infer the rating from the behavior of the user. For example, using the number of clicks, time spending seeing some product, number of publications, number of downloads, purchases, clinical usage, and experimental observation. A very, very known downgrade of implicit feedback is we don't actually have negative ratings. So for implicit data sets, we need to use specific methods to deal with this problem. And of course, when we use implicit feedback, it's always an attempt to guess what the user is thinking and actually thought about the product, because I can assist a film until the end and maybe I didn't like the film. Okay, so in biomedical recommender systems, most of the feedback is actually implicit because explicit biomedical ratings are very rare. Okay. About evaluation, it's a typical evaluation similar to machine learning, and the goal here is to evaluate how well a recommender system predicts relevant items for users. We can have offline evaluation with historical data sets. Advantages: it's fast, it's reproducible if we have access to the data sets, and low cost. Okay. Limitations: it doesn't capture real user behavior because this is not done in real time and with real users for that specific time. We also have an online evaluation, which is very rare in biomedical fields and very difficult to perform. It will evaluate the systems with real users. The advantage it's a more realistic evaluation, and the limitation is expensive, it's time consuming, and we really need to deal with people here. One of the most used methods is A/B testing, which is done in several platforms. Okay, the evaluation setup, as I already told you, is mostly the same. We collect interaction data, split into training, testing, and sometimes into validation, train the model, generate recommendations, and compare the predictions with the ground truth. But there is a major difference here in the split into train and test set between machine learning methods and recommender system methods. In machine learning, uh, it's a split independent row. So usually we will split our data set by rows, use this part of the data set to train and use this part to evaluate the model. But as in recommender systems, we have this high sparse data set, and we have this matrix with users and items. We cannot do this type of split, okay, because it would be very difficult to train only with user one and user two and test, for example, in user three, okay, because we need information about user three to in our training set. So usually this is a split between interactions. Okay, it can be done by time, or it can be done simply by a threshold, or 80% for training and 20% for tests, but always related to the number of interactions that this user has with the items. The evaluations metrics can be divided mostly into rating prediction metrics. If the algorithm is trying to predict the rating, so for example, if I have a movie recommender system and I try to predict if the user is give a rating between 1 and 5, I can use mean absolute error and root mean square error to see if my predicted rating is closest to the real one, or I can use ranking metrics, which will evaluate in a list roughly how many relevant items I have in that list. But behind accuracy, we also usually serendipity, coverage, explainability, fairness, and robustness. So why recommender systems matter in biomedicine? Biomedical research is producing data at an unprecedented scale. Scientific publications, genomic sequences, clinical records, chemical databases, medical images, microbes. It's growing exponentially every year. We have an information overload problem, and we struggle to identify the most relevant information. Recommender systems address this challenge by automatically identifying items that are likely to be relevant to a user, to a task, or to a specific context. So, for example, drugs discovery, drugs reproposing, gene disease association prediction, scientific literature recommendation, precision medicine, some clinical decision support system, recommending biological control agents. We'll talk a little bit about this in the end, and personalized healthcare. But unlike traditional e-commerce recommenders, biomedical recommender systems operate on highly complex, heterogeneous, and knowledge-rich data. And we have more responsibility because if I recommend a movie that the user don't like, it's okay. Okay, the user don't like the movie, but nothing wrong comes from it, hopefully. But if I recommend a wrong gene, a wrong treatment, a wrong BCA, this can lead to spends and costs and time and lives So we have a different responsibility here in the recommendation. Challenges in biomedical recommender systems, the data sparsity. But again, I think this is transversal to all the recommendation system field. So the interaction between users and biomedical entities are limited and sometimes incomplete. And the cold start problem. New drugs, new diseases, new microbes, or researchers may have little interaction with the data. Okay, so we need to find new data sets to deal with this. Okay, another challenge is the heterogeneous data, because sometimes, even if we are dealing just with one field, we can have multiple different types of data. Okay, text, images, molecular structures, sequences, graphs, clinical records, all for the same recommendation, for the same recommendation approach. Another challenge is the explainability. Recommendations in healthcare and science must be interpretable and trustworthy, or other way the clinicians, researchers will not use our methods. And of course, we also have these ethical and privacy issues, because biomedical systems often involve sensitive patient and research data, private data, data that cannot be shared. And even if we are creating these nice knowledge graphs and these nice data sets, we cannot share them. That's very difficult to work with. Okay, limitations of the traditional approaches. I already told you these more or less, but more specific for the scientific domain. It's the cold start, the sparsity, and the missing explanation. Okay? And to try to mitigate these, we have graph recommender systems, which is the main topic that I'm here to talk about. So the main idea, we have these traditional recommender system models that we already saw, that are constructed as matrices. Okay, so usually we have a matrix with users represented in the rows and items represented in the columns. However, using these data structure, many relations may be lost. So, for example, for a movie recommendation, I will have user watches movie. User is friend with another user. Movie belongs to some gender, and movie is directed by some director. The matrix will capture this first structure here, this first relation, but the graph will capture all of these relations. So if we define a graph as E and E between nodes and edges, what will be my nodes and what would be my edges in a recommendation system approach? The nodes can be the users, the items, authors, papers, diseases, genes, microbes, pathogens, and the edges will be the, well, ratings. Let's call it like this. It can be the purchases, one rated as a citation, co-authors, inhibits, cause, okay, is a, so the edges can be a lot of different things. Now we can use simple graphs in recommender systems, user like item, or we can have knowledge graph recommenders, where we will have this semantic structure associated with. For example, researcher writes a paper, this paper cites another paper, and this paper is about a disease. Now, some recommendation approaches on graphs. Okay, I try to bring some different approaches that are currently being used. So, for example, we can use semantic similarity, specifically and very useful for content-based. Okay, so the idea here is to recommend entities that are semantically similar. Of course, for these approaches, we need to have an ontology. We have to have a domain from a specific field to actually calculate the semantic similarity. We can use path-based methods, which we'll recommend through graph connectivity. So our recommendation can be finding meaningful connections between the entities. We can have embedding methods, which learn latent representations and will represent the entities and the relations as a vector. And it will recommend based on this vector similarity, and it's very useful for collaborative filtering, as well as the graph neural networks, which will learn the representation through neighbor aggregation. This is kind of a timeline of the use of graphs in recommended systems. The topic is not actually new, okay? So one of the first papers about using graphs in recommended systems is from 2002, sorry. But of course, the field evolved to link prediction recommendations, random walk recommendations, graph embeddings, graph neural networks, and most recently in 2020, this light GCN that I put here because it's still one of the most used approaches in graph recommender systems. So as I was saying, one of the first graph recommender systems was this paper, a graph-based recommender system for digital libraries. The main idea here was to use a user as nodes, books as nodes, user-book interactions as edges, user-user similarity as edges, and book-book similarity also as edges. And the recommendation becomes a graph inference problem, okay? So I screenshot this from the paper to show the simplicity of the first approach. Okay, but if we move on to light GCN, a much more recent approach, the architecture of light GCN is a simplified version of a standard graph convolutional network. Specifically designed to be more concise and more appropriate for collaborative filtering. Here, users are nodes, items are nodes, and the interactions are the edges. But if you look here at the architecture, it's much more complicated than the first one. So, and of course, with much better results. But like GCN, the main idea, it keeps the essentials operations, neighborhood aggregation. A user embedding is updated using the embeddings of the items. The items embeddings are updating using the embeddings of the users they interacted with. After several propagations layers, as we can see here, LightGCN combines the embeddings from different layers to obtain the final user item representation. And usually the recommendation is done using by a dot product. So it's actually a very simple method, but much more complicated than the previous one. Okay, this is a graph extracted from a survey on recommender systems for biomedical items and life and health sciences to show you that graph recommender systems are used in biomedical fields. Okay, so for example, in this graph, we can see that in the chemistry field, we have knowledge graphs. In the genetic field, we have some knowledge graphs, and also in health, in hybrid and other types of recommendation approaches. But in this survey specifically, from the 47 articles, there were 13 works using the knowledge graphs. So these are already being applied to biomedical fields and recommender systems. This timeline here is also from a very recent survey, a survey on recommender systems using graph neural networks. But I really like to show this because it shows the evolution of recommender systems, starting from classic models. Okay, so simple collaborative filterings using simple KNNs with similarity metrics, which, by the way, are still used as baselines. Okay, then the revolution of the deep learning and recommender systems started to apply neural networks, sequential modelings with the RNNs and LSTMs and so on. But actually, if you see the state of the art nowadays, most of the recommender systems approaches are using graph-based models. Okay, uh, and of course, more recently, um, we are putting together LLMs and knowledge graphs. Okay, so it's a very very edge field of study in recommender systems. Okay, now I have some use cases to show you about the use of knowledge graphs in specific works developed here in our group. I will start with an OntoChem hack, an hybrid semantic recommender system for chemical compounds. The goal here was to develop a hybrid recommender system for chemical compounds, but the main idea was to use semantic similarity between the chemical compounds for create a content-based algorithm. And we wanted to see if combining these with state-of-the-art collaborative filtering algorithms, we could improve the final results. Just a bit. So this is the general methodology. The collaborative filtering part, the content-based and the hybrid. Okay, so for the collaborative filtering approaches, we selected the alternating least squares and the Bayesian personalized ranking approach because these approaches were developed specifically for implicit feedback data sets, and the data sets that we are using in this study are with implicit feedback. So, and for the content-based part, we developed this approach based on the semantic similarity between the chemical compounds on the CABI ontology. Okay, so for this specific case, we already had an ontology to work with. Okay, how does this work? It's a very simple approach. So imagine that you are a user, and by the way, the users here in this data set are researchers. So but imagine that you are a researcher. Your trained data include chemical compounds that you already worked with. But now we want to, the algorithm want to see if caffeine would be a nice chemical compound to recommend to this user. So we calculate the semantic similarity between caffeine and each one of the entities in the training set. In this case, we used three different metrics, Resnick, Lin, and Jiang and Conrad. We got more than 114 millions of semantic similarity. So in the time it took us like 1 week to run all of these similarities between the chemical compounds. Okay, and the final score for caffeine would be the mean between the similarity divided by the number of training chemical compounds. For creating the hybrid, we used two very simple metrics. The product between the scores from CF and CB, and the mean between the scores. Okay, so here we didn't try to standardize the scores because we really wanted to see what would happen combining these scores, the raw scores. Okay. The evaluation setup, okay, we use this data set here. It's called Kern 20. 20 because we are only using users with 20 or more chemical compounds associated to. We have more or less 2,000 users, 16,000 chemical compounds, and more than 100 ratings. We tested different types of combinations between collaborative filtering, content-based, and the hybridization metrics. We used cross-validation, and we tested this for precision recall, reciprocal rank, and normalized content and DCG. And the results was that the hybrid got the best metrics for precision recall and mean reciprocal rank, and also for the MDCG. So in this case, the use of an ontology actually improves the metrics for the algorithms separately. Now another approach. This is more or less similar to the previous one, but it was applied to sequential recommendations. Okay, so this method is called SEAN, sequential enriched datasets for sequence-aware recommendations. So one thing that we noticed is in the literature, some items, well, not some, all the items does not have the same interest to a specific researcher depending on the time. So this is, for example, for paracetamol, the number of research articles on PubMed, and you can see fluctuation here. Okay. So the goal was to demonstrate first that sequence-aware data sets are better for recommending the next best item in scientific fields. But the second goal was to improve the results of these sequence-aware algorithms by enriching the sequence of the data set with the n most similar items. As I think you already know where this goes, these n most similar items were calculated using the semantic similarity. Okay, so for the first part, we have this data set with user item and rating. We create this second data set with user item rating and the year where this triplet was found in a paper. Okay, so now we can have a sequence. So instead of this matrix, we will have this timeline here. Okay, so for this user, in 84, the user wrote a paper about this chemical compound. In 2010, about this one. 2016 about this. And so what would be the best next item for this user? We tested different algorithms, the most popular, ALS, and we tested the BERT4HEC, which is a specific algorithm for sequence-aware recommendations. We, of course, tested these algorithms with the sequence and with a shuffle of the sequence. Next, we actually introduced in our sequence one most similar item. So for example, here for the original data set would be something like this. And in the enriched data set, we would calculate the most similar item to this one and add this to the sequence and pass this to the sequence-aware algorithm. We tested this with different number of items added, 1, 5, and we also tested either adding random items that were not similar to the ones in the data set. Okay, so the first results using the sequence got us best results comparing with the non-sequence. And when we tested adding one more a similar item to the original data set, we also improved the results for hit rate and DCG. Okay, so in this specific case, we tested this with two data sets. I'm not talking a lot about the second one because it was for astronomical objects, so a very different data set from the biomedical field. But for both data sets, we got the best results when we add to our sequence one more similar item. Okay. Now, I would like to talk about, and this is the last use case that I have, and this is my current work. It's called Plant Pathorec, and this is a recommender system for biological control agents against plant pathogens. So the motivation for this work was that crop diseases are caused by bacteria and by fungi, and this is a major threat to global security in food, and this leads to a lot of agricultural losses. And of course, there are a lot of chemical pesticides being used, which are not very good for the environment and for our health. So the idea and what would be better, it was to use biological agent controls, and these beneficial inhibit plants pathogens without the problem of the chemical pesticides. Okay. So what we want with this specific project, we want to accelerate the discovery of these new BCAs by recommending new microbes with potential to inhibit these plant pathogens. But we also are developing a second part to recommend already commercial products to the farmers. Okay, how do we do this with the recommender systems? So we want to generate standardized data sets of micropathogen interactions coming from the literature. Okay, and we want to explore the sequential and the complex relations between these items using sequence-aware recommendations and graph recommendation algorithms. Okay? This is the main methodology. I'm going to talk a little bit about this first part here, but the final product of this project is actually a platform for farmers, researchers, where these users will have access to some recommendations on what to study and what to use. Okay, so for the first part of the methodology, so the first goal was to collect a data set. We have a list of microbes and we have a list of pathogens. So first we retrieve articles from PubMed related with the pathogens. We use name entity recognition to extract microbes that are in these articles. And then we created, using this methodology here, the libretti, we create this pathogen microbe rating data set and a lot of more information extracting from the literature. And then we use relation extraction methods to extract the relation between the pathogen and the microbe that are in these research articles. So in this case, I'm using as users the pathogens and as items the microbes, and my rating would be just inhibits or not one specific, the microbe inhibits or not a specific pathogen. After this, the idea is to create a knowledge graph and apply graph recommendation algorithms. We already have some results. This is just a screenshot of the most recent database. Okay, we have a lot of more information. I just connected everything here. But for example, we can find microbe ID, which is an internal ID, a microbe name, the pathogen ID and name, the PubMed ID, where we found this microbe and this pathogen, the year of the paper, the relation extracted from these two, and also the crop. Because most of the papers actually are directed to crops. So we need to identify the crop, the pathogen, and the microbe. Okay. In this first database, we have 432 pathogens, 7,126 microbes, and roughly more than 13,000 relations of antagonist and agonist. But we have a high sparsity level here, so 99%. For the first test, we use this bipartite graph, a very simple knowledge graph with pathogen and microbes as nodes and the edges just as the relation antagonist. But the idea, and we have this information, we just need to perform the tests, is to create this large knowledge graph where we will have the pathogen, the microbe, but also the crop, the article, the disease, and also the taxonomy, the genus, the family, all the taxonomy for both pathogens and microbes. Okay. In the first tests, we evaluated a simple collaborative filtering, KNN, with a cosine similarity, a BPR, light GCN, a neural graph collaborative filtering, and GAE. And these are actually the first results for precision and recall. We are testing the top 1, 5, and 10, but we have more. And actually, with this simple graph, like GCN got the best results for all of the metrics. Okay. But what I really like to analyze in these results was the mean hits at 100. I will explain why. But for example, using light GCN, all of the pathogens has a relevant microbes included in the top 100. Okay, why is this relevant? Okay, this is roughly the laboratory pipeline of creating new BCAs or discovering new BCAs. So we have a diseased plant sample, we have the collection of candidate beneficial microbes, and we are working here. Then we move on to in vitro antagonist screening, greenhouse field trials, formulation, registration, and application. And this process can take as long as 10 years. Okay? And in this step here, thousands of candidates are usually tested. So if we could recommend 100, just 100, and two of them were actually relevant to treat this plant pathogen, that would be a win-win. Okay, so concluding, I think I'm running a little out of time. Scientific discovery can be viewed as a recommendation problem. Knowledge graphs enrich recommender system. Graph-based methods are transforming the recommendations. And in the future, we need to improve these knowledge graphs because the more information we have in our knowledge graph, the better will be our recommendations. We need to work in explainability, and we need to increase the confidence of the users. Okay, thank you so much. Let me know if you have some questions.